Okay, in our final section for Chapter 9, we're going to deal with hypothesis test for the difference between two means, but we're going to look at paired samples. Now, if you recall, the paired samples are dependent samples, either using the same sample, a single sample, with two different treatments, or we have items that are naturally paired together, and we select those pairs, and we put one pair in one sample, one item of the pair in one sample, the other item of the pair in the second sample. So let's take a look here. We're going to perform the test with matched samples using the p-value. We're also going to perform it using critical values, and then we're going to construct a confidence interval for paired samples. So p-value method. The nice thing about paired samples is we're not testing the two different samples, the two different treatments. What we're testing is the difference of the two treatments. So the difference of each pair becomes the data point, and you'll see that as we do the examples here. So a sample of 8 automobiles were run to determine their mileage in miles per gallon. Then each car was given a tune-up and run again, and then measured the mileage a second time. So here what we have is a single sample that's been used for two treatments. So we had the first treatment was with no tune-up, before the tune-up, measured the miles per gallon, and then they performed a treatment, they performed the tune-up and measured the miles per gallon a second time. And so this is typical of a paired sample where you have a before treatment and an after treatment. Or a before sample, I should say, and an after sample. So the sample mean mileage was higher than after the tune-up. It was higher after the tune-up, but we would like to determine how strong the evidence is that the population mean mileage is higher after the tune-up. Now, we could have found the mean of each sample, the before and the after, and tested them like we did in section 1 of this chapter. However, that would be inappropriate since it was the same sample used. That method only works if it's independent samples. Since these are not independent samples, it's actually the same sample used twice, it is more appropriate, statistically more significant to use a paired sample test. So the first thing we do is find the difference. So here we're going to do the after minus the before. So it's 1 minus 2 here. And we get a difference of 1.68, 0.87, and so on for each car, each of the 8 cars. This is the sample that we are testing right here, is the difference. So that is really what we're testing. And what we're testing is to see if the mean of those differences is equal to 0. So if we note the population mean mileage before the tune-up by mu1, population after by mu2, we are interested in that difference. Now here they're saying mu1 minus mu2, but up here we did, yeah, they did mu2 minus mu1 to get these. So they're a little mixed up here because they did the after minus the before, and here they're saying before minus after. But these are paired samples, and the mean difference is the mu d. So mu d is our mean difference, but again, they're listing it backwards here. Otherwise, these would be negatives here because the before is smaller than the after. But again, before performing this test, we need to define all those things. Again, they got that backwards here. So anyway, using the following notation. D bar is the mean of the sample of differences. D is the sample of differences. D bar is the mean of that sample. SD is the standard deviation of those differences. And mu D is the population mean for the differences of all cars before and after tune-ups. So therefore, our method for testing is going to be a paired test. We're going to test mu D, and the usual method for testing a single population mean. It requires the following. One, we have to have those random samples of matched pairs. So the matched pairs were actually set up after the random sample was taken, since we set a single sample and used it twice here. So we just took a random sample, did before and after, so the data naturally falls into pairs. But there might be other cases where we actually have to choose paired items. Like you might use twins to test, effects of vitamins or whatever. Put one twin goes into sample one, the other twin goes into sample two. But there again, the data is the link between them, the difference between their performance. So our p-value method here, we state our hypotheses. The null hypothesis will always be that the mean difference equals 0. So mu d equals 0. And the alternative, of course, depends on what it is we're trying to test or what our intentions are with it. Our test statistic is going to be that just we're testing that single sample, that sample of differences. So it's going to be mu d, or d bar, I should say, minus 0. Minus mu 0 is always going to be 0. And then our standard deviation of that set of differences divided by the square root of the sample size. And then, of course, yes, we can find the p-value using the curve. We interpret the p-value and state our conclusion. So using this data here about improving our gas mileage in the cars, they selected here alpha of 0.01, so a 0.01 significance level. So we first to check the assumptions. We do have random samples. Now they're smaller than 30, so since the sample size is smaller than 30, we need to know that the population is approximately normally distributed. Again, we check this for skewness. If we do the dot plot here, it doesn't appear to be overloaded on one side or the other. Now, it's not a beautiful distribution, but it's not strongly skewed. Not any like major outliers that stick way out. And not like a bunch of points on one end or the other. Like I said, it's not beautiful and even or anything like that, but it's not strongly skewed. So we'll go ahead and say that we're okay to proceed here. Our hypotheses. Like I said, the null hypothesis is almost always the mean difference is equal to 0. And here we want to say that the difference, that the mileage increases afterwards. So the mean difference is greater than 0 is our alternative. Our significance level, as we chose, was 0.01. Calculate the test statistic. Well, from our set of differences, back here, they found the mean and standard deviation of this set of numbers. The mean was 1.20625 and the standard deviation 0.37317. So our test statistic is found by taking that sample mean minus 0 and then that sample standard deviation divided by the square root of our sample size, square root of 8. We get a test statistic of 9.1427. Now, that's test statistic. If you're thinking critical values, that's a pretty large test statistic. So I'm thinking we're going to reject here. We should get a pretty small p-value. Now our null hypothesis here is greater than. So on our curve, we're going to be looking at this tail up here. Well, 9.147 is way out there. So let's take a look here, computing the p-value. So again, we're looking at this curve. 9.1427. And I want to know what's probably being greater than 9.1427. So on my calculator, I'm using an inverse normal. Oops, sorry. Not an inverse normal. I'm going to try that again. I would use a normal CDF. 9.1427 to positive infinity. So 1e99. Again, I could have used the 6 nines as well. 999999 for positive infinity. And the mean is 0, standard deviation is 1, because we're looking at standard normal. So I don't need to put those in. The calculator will assume those. Now I'm getting 3.09 times 10 to the negative 20th. So that's literally a decimal point followed by 19 zeros and then a 3. Now they're giving 0.0000193. So again, it's really, really small. Either way. Oh, sorry. That's why I didn't have the right one. Remember, this is always a t-test when we're dealing with paired samples, so I shouldn't have been using normal there. Should have been using the t-distribution. So TCDF is 6. So let's put in the point 9.1427. And my positive infinity I need to have my degrees of freedom in here, which is going to be 7. There we go. So that's what we're getting there. So it's times 10, 1.925 times 10 to the negative fifth. So move that decimal point over 5 spots. It is decimal point 40193. So that is why my first calculation was off, is we have to use the t-distribution because this is a t-test. So interpreting the p-value. Since our p-value of 0.0000193 is less than alpha of 0.01, we do reject HO. We reject the null hypothesis, and therefore we can conclude that there is a difference in gas mileage before and after. So we can include the gas mileage does increase after a tune-up. So yeah, you do have to be careful. Like I said, like you saw, I screwed up there and I tried to use the normal distribution to find the p-value. You gotta be careful. You can't. This is going to be a t-distribution. As we had mentioned earlier, anytime we're doing the test for two population means, we're going to be using a t instead of z. The only time we're going to use the z is for proportions, at least when we're doing with 2 proportions, because we always use z with proportions. Now also, you looked at those differences. It didn't appear to be a very large difference. That's one of the advantages of the paired test, is it kind of looks at it under a microscope. It gets a little bit closer view of it. So here, if we had done this as independent samples and had those differences, we probably would not have had nearly as large of a test statistic and a much, much higher p-value. We would have been on the edge of accepting or rejecting this. So the paired test, again, it's more precise on its ability to discern between those differences. So it is a good thing to do the paired test when we have data like this. And it is the appropriate way to do this because those were definitely not independent samples. It was the same sample under 2 treatments. So let's do the match sample test using critical values. So there's our process again. It's the same process for doing hypothesis tests we've used for critical values all along. Set the hypotheses, set your confidence level, then find your critical values off of that. Compute the test statistic, and then compare to your rejection rule based on your critical values. So here we're looking at now for a sample of 9 automobiles, the mileage in thousands of miles, of which the original front brake pads were worn out, is 10% of the original thickness to 10% of their original thickness was measured, as was the mileage of the original, in which the original rear brake pads were worn down to 10% of the original thickness. So they're looking in thousands of miles how long it takes to wear the brake pads down. So they're comparing front brake pads to rear brake pads. And we're getting a difference here. So again, it looks like we're doing rear minus front to get that number. And that's what they're saying, rear minus front. So whatever they define the rear to be is going to be the larger number there. Let's see, can you conclude that the mean difference takes longer for the rear ones to wear out? And we're going to use a significance level of 0.05. So then we have to check our assumptions. Sample size is still small, and there's still only 9 cars here. So we plot those numbers. Now looking at this, you've got the big spike here in the middle. You got 3 of them that are the same, and then you got 2 on this side and 4 on this side. It looks to be slightly skewed, but not extremely skewed. This one would be on the edge. And this is the tough part about these tests. One of the tough parts is in these assumptions, because there's tests for skewness can be a long test in itself if we want to do a formal test for it. And we're trying not to get a huge add a huge extra number of steps to this process. So we use these dot plots. But this dot plot here might be a little tricky. I mean, I wouldn't blame you if you looked at this dot plot and said, it's skewed, I don't think we can do this test. This one's right on the edge. But let's assume that we can go ahead and do the test, that it's slightly skewed, but not extremely skewed. So let's go ahead and perform this test. So our hypotheses, and as always, the null hypothesis is going to be that the difference is 0, the mean difference is 0. And then we're saying that the rear is going to be larger than the front, or longer life than the front, so we're saying the mean difference is greater than 0. So the significance level, we already said, is going to be 0.05. So therefore, we're looking at the curve here. We're looking on the alternative is greater than, so greater than is the right tail up here. So I want to know what value gives us 0.05 here. Well, n is 9, so we're looking at 8 degrees of freedom. So if I were using the calculator for this, distribution, I would have to use the inverse t. This is 0.95. Remember, t always gives to the left, so 0.05 to the right of it. 0.95 would be to the left. And 8 degrees of freedom. 1.859, 1.860 it looks like, which is what they gave us for their critical value. Test statistic. The mean difference of that set, if we look back here, the mean of that set and the standard deviation of that set is what we're testing. The mean is 10.144, a standard deviation of 1.0333. Okay, you got a typo here, it looks like. This should be 10.1444, and this should be 1.0333. Here, I'm going to pause here. I'm going to run this through the calculator. I'm going to see which numbers are actually used for that test statistic. Okay, so I'm not sure how they came up with these numbers that they put in here, but those are not the right numbers. It should be 10.1444 over 1.0333 divided by the square root of 9. I mean, they calculated the 60.28 did come from these numbers, but those are not correct. And that should, if they divide that out, this should come out to 29.45. Now, either way, that is still greater than our critical value. Remember, our critical value was 1.860. And we would reject if the test statistics is bigger than 1.860. Since this is a right tail test, we reject if we are larger, if we're on the larger than side, greater than side. So we would still reject HO at the 0.05 level of significance of alpha. So we will still conclude that the mean time for rear brakes to wear out is longer than the mean for the front brakes. Now 29, by the way, is a large, 29.45 is still a large test statistic. So that's saying there is a significant, a huge difference. Not just enough to be statistically significant, but there is a huge difference in life between the front and rear brake pads. Now we're going to look at the confidence intervals. So the confidence intervals, we're just making an interval for a single sample. Now, I want to go back here for a second, and I want to show you how to do this test. We're going to do this test here using the calculator. The way we would do that, now if you're using Excel, you just put columns in Excel the same way. You'd have to do the calculations by hand, and I'll do a supplement for that for us. But let's go to Stats, Edit, and then Edit again. I'm going to clear out my list. So just remember, I highlight the top of the list, the name at the top of the list, hit clear and enter to clear out the whole list. So I'm going to put in here 42.7. Actually, you know, I should probably put in my front brake pads first. So 32.8, 26.6, 35.6, 36.4. Now you might be looking at this wondering, well, how are these paired? Well, what they did for each of these, this is a car, and on one car, they measured the front brake pads and the rear brake pads, so that it is just a single sample measuring two different attributes within that same sample. So it's definitely a paired sample, and they're definitely not independent. Now, you might wonder, well, driving habits and all that come into play for brake pad wear. And that's why the match sample is appropriate here, because that car has been driven by the front brakes and rear brakes have gone through the same experience, same driving experience. So it is most appropriate to use a match sample for this type of a test, for this case. Just a few more to go here. So list 2 here is the rear brakes. Now in L1, what I'm going to do is I'm going to go up to L1. I'm going to highlight it, and I'm going to do second L2 minus second L1. We want to do rear minus front was what it was telling us to do. That fills in those numbers. Now notice those numbers there should be the same as this bottom list here. So I'm going to exit out of here, and the test I would perform, do stat, test, and this is just going to be a regular t-test. Instead of stats, so I'm going to use data because I have the data listed in there. My hypothesized difference is 0. It's list 2, so I'm going to do second, or not list 2, list 3 is where the differences are. So I'm going to put list 3 in there. Frequency is always 1. My alternative here is greater than 0. So I'm going to calculate. And there we go. It gives me the test. Now it's giving us the same one they had there, the 60.27. So I'm thinking maybe they wrote down their mean and standard deviation wrong. X bar 10.47. Now looks to be exactly what happened here. Is it wasn't that they put the wrong numbers in here, they put the wrong numbers up here. So this really was this mean the mean difference here should have been 10.478. And this should have been 0.5215. So the wrong numbers were up there, not down here. So the 60.28 is the correct test statistic, which is even worse than the 29.45. I mean, the p-value here would be absolutely tiny. So, I mean, we rejected, not only did we reject, but we really blew this one out of the water. And as you can see on the calculator, we get that same result, that test statistic of the 60.28. P-value, we haven't done p-value yet for this one. We didn't do p-value for this one, I should say, but 3.19 times 10 to the negative 12. So that's the decimal point followed by 11 zeros and then the 319. I'll round it to. So there is the test on the calculator. So now let's look at our confidence intervals. So we select 16 volunteers, and they were given a test in which they had to push a button in response to the appearance of an image on the screen. The reaction times are measured. Then subjects consume enough alcohol to raise their blood alcohol to 0.05, and then they do the test again. So again, there's 2 samples. One sample, but 2 samples of data from that same sample of subjects, before and after again. Here's our data. So this is the uninhibited set here with no alcohol, assuming none of them had any alcohol consumed before they arrived. And then this is the after getting the 0.05. And then here's our difference. This is our set of differences. Now you can see there are a couple of them that were actually quicker once they'd had some alcohol in them. So now, again, the mean of the first sample is 81.3. The mean of the second sample, 74.8. Remember, the sample 2 was the no alcohol. And sample 1 was after the 0.05%. So the means show a difference. The mean is definitely larger, or looks larger here after they consume the alcohol. But again, there's that chance that we just happen to randomly select people for our test who are easily impaired by alcohol. So we have to go through and perform the test. Independent samples would not be appropriate because it was the same set of people just done with two different treatments. So we have to use the match sample. So we're going to be using D bar. Now it's saying here D bar is x1 minus x2. That's not really true. It's going to be each individual item that we're testing, not the difference in the means. So the mean difference should not necessarily be the same as the difference of the means here. So I don't care much for the notation there, but let's go ahead and do our interval here. So the confidence, so what they're saying is since there's that relationship between the mean difference and the difference of the means, that that confidence interval for the mean difference is representing the confidence interval for the difference of the means, in this case, since it is a paired sample. So let's construct that confidence interval. So suppose we want to construct the confidence interval for the population mean increase, the mean difference for our experiment. So the method for computing a confidence interval is the same as computing a confidence interval for a single population mean, using a t-interval, of course, because paired samples are a t-distribution. So you find that mean and standard deviation for the sample of differences. So the point estimate is that mean, which was the 10 point, well, for this set, 6.5 is that difference, is the mean of those differences, I should say. And then you have to use the standard deviation divided by the sample size, the square root of the sample size, and then the critical value to get a standard error and a margin of error here. So you have to find that margin of error. So let's go through and have them take us through that process. So it is a 95% interval, so our critical value, remember again, 95% is in the middle here. So you got 0.025 on each side, or 2.5% on each size here. So this is 0.025 here, 0.975 here, which gives us a 1.96 critical value. We are less than 30, so we check for skewness. Again, there appears to be a slight skew here, but no major skew, so it's okay to go ahead and make our confidence interval. Now, they did a box plot here instead of a dot plot because we're getting a larger number of points. But there are 16 points here instead of just 8 or 10 points. So it's a little bit easier to see with the box plot. 8 or 10 points, you can't even hardly make a box plot because there isn't enough points really to give you much of a shape here. But you could have done a dot plot here as well as the box plot. It would give you the same result. So, as we saw, our mean difference is 6.5. Standard deviation of those differences looks like it's 9.93311. Critical value, they're finding, oh yeah, it can't be 1.96. This is not, get rid of that. This is not a Z interval. It is a T interval, so we have to use the T distribution. 15 degrees of freedom because the sample size is 16. So 15 degrees of freedom, 0.9 or 0.975. Let's go ahead and do that on the calculator since I seem to. You can see I am, doing that T interval more often than I should. In fact, I don't want, or using the Z distribution instead of the T distribution. It is really easy to make that mistake. So let's go back and use the T distribution. 0.975, and this is 15 degrees of freedom because the sample size is 16. And there we do get 2.131, which is what they had. Oops, where are we? So they get the 2.131, which is what we just got. So they're going to take standard error is the 9.93311, the standard deviation of those differences, divided by the square root of 16. That's the square root of the sample size. So we get a standard error of 2.48328. Multiply that by that critical value of t, 2.131, so we get a margin of error of 5.292. So our interval is going to be that point estimate of 6.5 minus 5.292, which is 1.2. And then our point estimate of 6.5 plus the 5.292 is 11.8. Now what we see here, this interval does not contain 0. So this interval is actually providing evidence that there is a difference. So we can say that we're 95% confident that the mean difference is between 1.2 and 11.8. And again, since this confidence interval does not contain 0, and all the values of the confidence interval are positive, we can be fairly certain that the reaction time is greater after you've consumed that amount of alcohol. Matched samples generally give a smaller margin of error than paired samples do. So let's go back, and I'm going to do on the calculator here to show that our margin of error is going to be small. Well, let's go through their example here. They're taking the same data. They have the mean as set 1 and the mean as set 2. And then here they found the standard deviation as set 1 is 22.71. Standard deviation as set 2 is 27.39. And if they use that to do the margin of error, to get the standard error from those standard deviations, we get standard error of 8.90 times compare that to the standard error for the paired samples, only 2.48. So this is going to give you 4 times the margin of error, which if we did that, then we're going to contain 0. And that's not going to be a great... it's going to contain 0, so we won't be able to make any conclusions off of it. So as we said before, the t-sample, the paired samples, look at the data a little more closely, and they zero in and they highlight those differences a little bit better. So whereas using an independent sample test, you would not have had evidence against them being the same. You would not have had evidence to reject a null hypothesis. Using the matched samples or paired samples, you look a little bit closer and you are able to gather enough evidence to reject a null hypothesis. So let's go back to this, these samples here from the brake pads. Remember, this is the front brake pads in L1, L2 is the rear brake pads, and L3 is the differences. Let's perform a confidence interval for the difference for two sample t interval. That's what I want right there. We have data is what we're going to use. List 1 is the first one. List 2 is the second set. In fact, I could change that around. Let's do second L2 to be consistent, and second L1, because we were doing the rear minus the front. Let's do 0.95 significance level or 95% confidence. Pooled is no, and then we're going to click calculate. So it's from 5.6 to 15.3. If I go back and perform this as just a t-test or t-interval on the differences, there's my t-interval. That difference is in L3, so we're good to go there. Remember, frequency is always 1 here for what we're going to do. Hit calculate. It's actually 10.07 to 10.879, so it's a much, much narrower range. Remember, the other one was 5 to 15, a much wider range. So you can see using the matched samples, the paired samples, really narrows down that interval. So it's actually, not only is it more appropriate to use the matched samples, it's actually to your advantage to use the matched samples because you get a much more precise test. Remember, precision is the ability to tell the difference between items that are similar. It gives you a higher level of precision because you can really break apart the data and you can highlight those differences in the data. So what we learned here, we did a matched sample, paired samples using a p-value method, and we did matched sample tests using critical values. Then we also conducted the confidence interval for the paired samples. That is it for Chapter 9, so you guys have a great week.